My name is Nebojša Dončov. I am Vice Dean for Science at the Faculty of Electronic Engineering. And I would like to use this opportunity to welcome you all at the Faculty of Electronic Engineering. This is our largest amphitheater. And to wish you a pleasant stay at the faculty and a very successful event career path in semiconductor industry. At the beginning, I would like to thank organizers of this event for inviting not just students of our faculty, but also students from other faculties in the area of electrical engineering and computer science in Serbia, students from Faculty of Technical Sciences in Novi Sad and Čačak, and School of Electrical Engineering in Belgrade. Also, I would like to thank all keynote speakers and the participants in panels and the presentations and the company representatives that contribute to this event. I would like also to use this opportunity to say a few words about the faculty. The Faculty of Electronic Engineering has a very long tradition. Next week, we will celebrate 62 years of existence. We started first in 1960 as a department of electronics within the technical science faculty. And 8 years later, 1968, we became Faculty of Electronic Engineering. More than 8,000 students graduated at this faculty in this 62 years existence. More than 1,000 master students, and I believe around 210 students successfully defended their PhD thesis. We are officially accredited to conduct study programs at all three levels of studies: bachelor, master, and doctoral academic level. And we are also officially accredited as a scientific research organization to collaborate on many either domestic or EA-funded projects like Science Fund and Fund for Innovation Activities in Serbia, funds financed by the European Commission like Horizon 2020 and Horizon Europe. And we do have a lot of either domestic or internationally funded projects. We are also very proud that we have very successful cooperation with industry, not just industry that is based in Niš in this part of Serbia, but we do have partners all around the world. We have companies in Switzerland, Germany, USA, with whom we have a very successful collaboration and cooperation. We see this event, this is the first of this kind of event, but hopefully it will last for years to come. We see this event as an opportunity to show to you, students, what opportunities you have, not just in computer science, but in other disciplines like electronics, microelectronics, and etc. So I plan to be brief, so maybe I start to talk a bit more, but I will finish now. Again, I wish you pleasant stay and fruitful event, and hopefully we will see this event to last in years to come. Thank you.
So good morning, everyone. Thank you for having me. It's such a pleasure to be part of this inaugural event. And I want you to know how very unique this particular program is. So the fact that you have so many companies coming together, Serbian companies, many of them competitors, to come together to cooperate to be here today. And not only at the company level, but most importantly at the individual level. And then to have so many universities coming together to put together this program. I mean, it is really unique, and I'm very proud to be part of it. So I'm Jody Shelton, and I am the co-founder and CEO of the Global Semiconductor Alliance. So this is an organization started about 20 years ago, and maybe like 25 years ago now. And this organization brings together leaders of the semiconductor industry to discuss topical issues of the day, to collaborate, to have a platform where they can get together to solve problems, and to highlight the many, many opportunities in the industry. So really the one thing that I want you to take away from who GSA is we're advocates for this industry. I mean, we're here to tell the students what an amazing industry this is and that you should really want to be part of it. So that's what I'm going to be discussing today. So first of all, I would like to discuss that semiconductors are a critical part of modern life. And for many years that I've been part of the industry, people ignored that fact. And so you had leaders in this industry that were really, baffled and lamented about how difficult it was for people to understand this foundational technology, foundational to the modern world that has helped make life better for people all around the world, makes things more efficient and productive. And so, of course, during COVID, people became very aware of the semiconductor industry. So now, or really probably a couple of years before COVID, but it was exacerbated during that point in time. So now you have Wall Street, you have boardrooms, and you have actually capitals all around the world that understand how critical semiconductors are. And this understanding the criticality of semiconductors is actually important for the industry because we want to attract young people like yourself to be part of this industry. And the more that you understand what it is, and the more that perhaps the people, your peers around you, or your spouse or your parents, the more that they understand what this industry is, the easier it is to make that decision to join the industry. If you can tell, your mom and dad that, if I join the industry, chances are you'll get a car sooner because I'll be designing the chips for it. So I think that it ends up being very important for people on the outside of the industry to understand the impact. And of course, it is important to technology and to the digital part of the modern world, but it's also really important for the economy. So semiconductors have about an 8 trillion, and this is actually, this information is a little bit dated, but probably have about an $8 trillion to $9 trillion impact on the global economy. So I think that it's very important to support this industry and, of course, at some point in time for you to be part of it. So also, 50 billion units, IoT units will be connected by 2030. So I think that that's an important sort of takeaway about the criticality and the importance of this industry. So why is it important for you to see what the criticality of the industry is? So I believe that it's important because there has simply never been a better time to be part of this industry. So if you understand the industry better, maybe you will be interested in joining it. So again, the many different technologies, whether it's artificial intelligence, whether it's quantum computing, whether it's the metaverse that we're going to hear about, all of these technologies that are enabled by the semiconductor industry. So what I'm here to tell you today is that the industry wants and needs you. So what we're looking for in this industry is critical thinkers, great designers, people that are willing to work together in a collaborative format to bring these technologies to fruition. So as the self-appointed ambassador, which I feel like I am, to this industry all around the world, we do want you to know that you're wanted and needed by this industry. So if you are considering electronic engineering, or mechanical engineering, or physics, or any of these types of technologies, we really need you to be part of the industry. And the other reason that we need you is that there are so many big problems that the world faces and that you probably worry about on a daily basis, whether it's climate change or endemic poverty. The technology coming out of the semiconductor industry is going to be the solution to these problems. So keep that in mind when you're thinking that you want to have a career that really makes an impact on the world that you're part of. So you can really help design those solutions to those many problems that I just talked about. You can be part of designing chips for carbon capture, for electric vehicles. You can be part of designing IoT chips that will look at the soil samples from Haiti to help the farmers decide when to plant crops. So you can be part of ending that kind of endemic poverty that we see in countries like Haiti. So again, if you're looking for a career where you can have a big impact on the world, then we want you to be part of this industry. So the semiconductor industry is also very interested now in having a diverse workforce. So this industry has goals and aspirations to be at $1 trillion industry in the next 5 to 10 years. So if that's going to happen, we need to make sure that we're an attractive industry for the young women in this audience as well. And I think that you will find that the semiconductor industry is very open to welcoming female engineers. Personally, I believe that the world is your oyster. And for the women here, I think it's the perfect career opportunity. And you're going to hear from several of the women on a panel in just a bit, and you will understand better about what it's like in the day in the life of a semiconductor engineer. So what the GSA started a few years ago was this Women's Leadership Initiative to make sure that we are being an attractive industry for female engineers. And so the goals and aspirations of this particular initiative is, first of all, to attract the young women that are already kind of STEM focused, on that STEM focused path at university, and make sure that you understand that this industry is a growing opportunity, that you can have an amazing career with not only growth opportunities, but have a great salary as well, right? Okay, we're going to have a great salary at V-Tool and these types of companies. So anyway, so the second objective of this particular initiative is to make sure that the women that are in the industry are developed and see growth opportunities to be leaders in this industry. And again, you're going to hear from some of those young women today. And I think that indeed there are so many opportunities to lead for women in this industry. And then the third objective is to make sure that female-owned companies that are in the semiconductor industry are getting the attention and the VC funding that they need to go to the next level. And we do have several female CEOs on our Women's Leadership Council that have young startups that we really want to make sure that the VC community is aware of. So one of the programs, of course, that we have is this university program. And again, I want you to know how unique that this particular program is, how that all of the universities have come together in the companies. And it's really, I really think is going to serve a model for the rest of the world. So we have programs at other universities in the US, and actually going to Cambridge this week as well to have a program. So what I wanted to end with is just kind of a few ideas about how you can build a successful career in this industry if you do decide to join it. So the first is to not only understand about the particular project and electronics that you're working on, a particular chip or maybe a verification of a particular chip, but to understand the big picture of where that chip is going in the markets, so that you can really understand and participate kind of in that bigger view of product development. So I think that that's very important. The second is, I think that you really need to understand as a young engineer, and especially the female engineers, that you really do have a lot of power to wield. Companies want to create environments that allow for females to do great innovation. So I think that you really do need to wield that power. And I think that you'll see a perfect example of the women doing that today. And then the next thing is to really build your brand and visibility. So we found in the industry that, although we want more women in the industry, and there certainly are not enough, the women that are here are really amazing, but they were kind of behind the curtain. And now we've got a program that really helps these women get the visibility that they deserve, and that we think that is very important, again, to attracting other women to this industry by having this visibility. So your own visibility and branding does matter. And I think that that's an important opportunity as you look at your career. And then the next is to build meaningful relationships with not only your peers here at university, but perhaps build a whole network of people that can help in your career. I always call it my personal board of directors. Like, I have people that I personally go to when I need advice on my career, when I maybe need financial advice, and I have my own set of kind of my personal board of directors. So maybe something that you think about as you begin your career. And then this last one I think is most important, and that is to be brave, to take chances and to really go after your dreams and to go after the hardest problem. So Lisa Su is a very famous female CEO in our industry and is the CEO of a company called AMD. And she has a story that when she first went to university, she went to MIT and she went and asked, what's the most difficult major at university? And they said, electrical engineering. So she goes, I'm in. And so if you watch her career, when she joined AMD was probably one of the most hated companies in this industry. I mean, it was really sort of on its last leg. Everybody thought that a CEO would come in and kind of revamp it a little bit and then sell it. And if you look at AMD today, it's one of the most respected companies in our industry, one of the fastest growing companies with some of the most exciting opportunities. And that's because Lisa Su was brave and took the chance on AMD and has really turned it around. So I hope that you will use that as an example, perhaps for your own career. So again, kind of concluding thoughts, I think that this is a very exciting industry for you to choose for your career. There's lots of opportunities, and there's lots of opportunities for the women that are here today to choose this industry. And if you choose it, as a student, we ask that you stay the course. We know that it's tough. We know that there's probably easier majors at this university. There may be even easier jobs when you get out. But this is a fulfilling job. It's one that you can have a big social impact on the world. And we hope that you will choose it. And be sure and go and look at our website, designthesolution.org, and you'll get lots of inspirational stories and lots of stats about joining this industry, what it will mean for your career long term. So thank you for having me, and I hope you enjoy the rest of the program. Thank you.
So, hello everyone. Yeah, so it's I'm very amazed to be here. So I mean, it's a big audience. So usually I don't have such a big audience to be honest. And I would like to start with a disclaimer first. So I mean, this is a conference which is organized by the Women Leadership Initiative, and so I'm not exactly a woman, and but there is a reason for that. So first, when Cadence was invited to present here, so we thought, okay, we have a Serbian engineer in our Munich office, so she's a kind of a role model, so she could come here and she could do this keynote. But we have currently at the same time now a Cadence Women Conference, which is going on in Israel. So therefore, she's now in Israel, and now so I had to take her job. And so then I was talking to my sister, and I said, well, so you know, I have now to come here and to present. And she said, Anton, it's not a problem. You're not a woman, but you are an ally. And I said, okay, good. I'm fine to being an ally. So therefore, yeah. So therefore, I'm here. Good. So first, I would like to ask you. So how many of you have heard about Cadence? So just hands up. Okay, so let's say half, a good half of people. Okay, good. So that means that now I have half an hour to explain what Cadence is doing in the huge ecosystem of microelectronics. And I mean, the ecosystem is really huge because I'm now 18 years in this industry, and sometimes it happens, I come to a conference or I come to a trade fair, and I realize that I don't know a single company there, because they are all doing microelectronics, but they are, for example, in manufacturing, and so we are not doing any manufacturing, or they are somewhere on a very high level of design, so this is also not what we are doing. But now I will try to explain in this half an hour what Cadence is doing and why it's also worth to apply for a position in this company. Good, so Cadence is doing EDA. So EDA stands for electronic design automation. And this means that this is the software which designers are using to develop integrated circuits or PCBs. So what you see here on this picture, so on the very top, so there's it's called an IP block. So this already is a block which contains some integrated circuits. So then we have an IC. So this is usually a system on a chip, so which contains different IP blocks. Then we have a package. So in a package, there can be one chip or one SoC or even several, and also a lot of other elements. And then finally, we have a PCB, a printed circuit board, so where different chips are mounted. And Cadence is developing software for all these design stages. So basically, you develop your IP block first, you develop your SoC, you develop package, you develop PCB, and for all of this, you can use the different Cadence software. Yeah, so there are two main parts of EDA. So there's the PCB EDA. So this is software for developing a printed circuit board. And then an IC EDA, so this is for the integrated circuit. So a PCB, probably you've all have seen a PCB. So if your mobile device is broken, so then you can just remove the display, and then you see something green there. So one is the battery, and the rest is the PCB with some chips on it. And then there's the IC. So IC is the integrated circuit. So this is something which is inside this black rectangles. And now if you remove the package, so then and you zoom in, so because in real life what you see here, this is 1 square millimeter, 2 square millimeters, so very, very tiny. And then if you zoom in, so then you find there are millions and billions of small devices inside. And so now some software needs to be created in order to place these devices, to connect these devices, to verify these devices that they are all working properly under different conditions, so different temperature, different voltage. So there are a lot of challenges to be accomplished till a chip is ready to function. So I would like to go with you quickly through the VLSI design flow. So VLSI stands for very large circuit integration. And so there are different stages. So the first stage is the system specification, then we have the architecture, then the functional design, synthesis, physical design, fabrication, and then finally packaging and testing. So now let's go step by step. So for example, we want to create a system, and the system can be as simple as a wristwatch. So first you start with the system specification. So what this wristwatch should do. So it should display time, it should set alarms, it should have a stopwatch, and also very important, what is the maximum cost of this design, so maximum production cost here. So once this specification is done, so for this you don't need Cadence software yet, so this can be done with a Word document or PowerPoint or Excel. But then you go into the architecture. So then you must understand, so for your specification of a system, so what kind of architecture the system should have. So it should have a plastic band, it should have a display, it should have control buttons, and then also it should have some kind of chips inside of it. And this is where we now go into the functional design. And in the functional design, you are using a hardware description language. So for example, Verilog or VHDL, in order to define so the functionality of the chip and also the content of the chip. So here there's an example how a Verilog code looks like. So you have different modules. In these modules, you have some inputs, you have some outputs, and then something happens inside the modules. Then you see also there's a clock, and the clock it has an edge, a positive edge. So every time when there is a clock signal coming in at the positive edge, so then something is happening. And in the yellow box, so you see that the two modules which have been specified, so they are instantiated here. So then they are basically doing something. Okay, so now you have this specification. So it's also called RTL, so register transfer logic. And now there's a step which is called synthesis, and then the synthesis step converts this description into so-called netlist. And netlist contains standard cells. And in the standard cells, these are the basic logic. For example, a not, or an and, or a nor, or an XOR. And so now the synthesis tool converts the Verilog description into this standard cells description. And there are different technologies in which a chip can be fabricated. So there are different manufacturers. So for example, Global Foundries or TSMC or XFAB or IHP. And they all provide a library which contains several hundreds of the standard cells. So therefore the synthesis selects so which cells should be taken from this library and included in the design. So for this, you already need cadence tools, which is called a genus. So this is the synthesis tool. So now you have a netlist, but all these standard cells, so they have to be placed somehow on a chip, because all of them, they have certain area, and then they have to be connected with each other. So it's a routing step. And the routing, there are not only just one level of routing, but up to 11 levels. So that means that there must be a tool which does the routing between the different standard cells. And the tool for this, which Cadence is offering, is called Innovus implementation system, or place and route tool. So first it places all these millions and billions of standard cells, and then it creates a routing, so which connects these cells. So of course it sounds simple, but the problem is that there's timing. So that means that there are these clock signals. So you know your processor in your computer, so it has, for example, 3 gigahertz, and then it must be ensured that the signals, they have enough time to get from one register to the other in the given amount of time. So this has to be verified. So there are billions of different passes that a signal can take. This has to be verified. Then also there is such things like energy consumption. So it can happen that a chip consumes too much energy, especially if it's a wearable, like a wristwatch. So then you have to verify that the power consumption is in a given specification. Then there are logical checks. For example, do you have some open signals, or do you have some shorted signals? So this also has to be verified. And then finally, when all this verification has happened, so then the outcome of this is a so-called GDS2 file. So it's basically like a very big image. So it can have like 50 gigabytes or even more. And this image is then transferred to manufacturing. And then the fab then creates a chip out of this description. So how does it look like? So here on the left side, on the top, so this is something. So this is how a transistor looks like in a tool which we call Virtuoso. So this is a tool for analog design in Cadence. So you see that so the green line, this is the gate, and the blue lines, this is source and drain. So then on the right side, on the top, so you see, so if you cut a chip vertically, so these are the different layers. So on the very bottom, so you see the transistors, and then the blue shapes, these are the vias. So these are the connections between the different routing layers. And then the purple layers, these are the metals. And so during the manufacturing step, so step by step, every of these layers is created. And there are several steps which are needed to create each of these layers. But today in the afternoon, so there will be a lecture about the manufacturing. And so then after this has been done, so if you now zoom very, very closely, so then you see the picture which is on the left bottom. So this is how a transistor looks like on a chip. So you see it's so you see the gates, you see the source and drain, and yeah, this, and so the size of this of the structure is maybe 100 nanometer or even 50 nanometer. So if you compare it with the thickness of human hair, so there are thousands of these structures which fit just on a human hair. And yeah, so finally on the right side on the bottom, so you see this is a complete wafer. So if you visit the booth of IMEC here, so you will see this wafer also in reality. And so then at the final step, the chips, there's a sewing process where the chips are sewed out of this wafer, then they are packaged, and then they can be delivered. Yeah, so here are package examples. So these are different packages for different requirements. So basically, a chip needs to be put into the package. So there can be also several chips in one package. It's also called system in a package. And now it's also becoming more and more important. So if you want to have a sure or a secure job in the industry, so you do package design. So here there's a large need for package designers. So chip design is very complex. You can compare it with the design of a modern plane, but the challenges are completely different. So usually for designing a plane, so this is like 10 to 15 years. So now a chip, usually you have a time for about 1 year for designing a chip. So for example, if you take a smartphone, so like an iPhone, so every year there's a new model of an iPhone which comes out, and every year there's a new processor in it. So basically every year the engineers of Apple, they have to design a new processor. And they do it usually in a new technology. So basically every 2 years there's a switch from a technology, so like from 20 nanometers to 60 nanometers to 10 nanometers to 7, 5. So next step will be 3. So every 2 years there's a change in technology. And then every technology also requires new tools, new software, because there are always new effects, and these effects need to be taken into account to ensure that the chip is working. So therefore, designers always need to learn about the new tools. Yeah, and then once you are finished with your chip, so then you immediately start working on the next generation. Yeah, and so this explains also why a chip is something very expensive to create. So therefore, you usually need a huge market. So just to make sure that the production and the design costs, you can get them back from the market. And now the question is, so what are the most expensive tasks for chip design? And so here I have so here are the different costs. So I hope you can see it. So that so the big portion of it is the yellow one, and yellow, this stands for verification. So verification is currently the most costly step of designing an IC. And why is it the case? Because I mean, a software, it's easy to fix. So you find a bug in the software, so then you just provide an update, and everyone is happy. With a chip, if a chip is already built in a system and the system is sold to somebody, so then just to get a new chip and put it again into the system to replace it. So this is something which is very, very expensive usually. So I mean, the car manufacturers, so you can imagine if there's an error in an automotive chip, so then till you get all the cars back into to manufacturing and then replace the chip, so it's a huge cost. So therefore, it's very important before a chip goes into fabrication that the chip doesn't have any errors. So therefore, there are many different ways so how to verify a chip. So there are different approaches. So here you see some of them. So There are formal analysis, there's digital simulator analysis, you have even a hardware, so which accelerates the execution of your Verilog code in order to find some errors. So you can already, so if you have a processor, so you can already start your operating system on a processor which not yet exists. So for this, you need this accelerator boxes. Okay, so you can do also FPGA. And so Cadence is providing software for all of these, software and hardware. So we are providing also these boxes called Palladium or Protium, for verification. But still, it's not really enough, because the verification complexity is rising faster than the design complexity. So when your design is 4 times more complex, your verification effort is 7 times more. So you have a gap here, and this gap you need either you have more engineers that can do the verification, but the problem is that I mean, verification engineers are now very wanted on the job market, and there are always not enough verification engineers. So basically all companies which are doing chip design, so they are constantly searching for verification engineers. The other approach is to try to automate verification as well. And here, one approach is to use machine learning for that. And here I can show you some example how verification software uses machine learning for simplifying verification. So here an example is formal verification. So formal verification is basically a mathematical proof that the circuit that you have designed is correct. And there are several algorithms which can be used for verification. But the problem is that not all designs are converging on a particular algorithm. So that means that for different designs, you need different algorithms. And so far, the engineer was supposed to find the right algorithm for the right design. And this is something that our engineers said this could be solved using machine learning. So first, what we did was supervised learning. So basically, there were many designs available, and then our engineers, they have labeled this design, so which design fits to which algorithm, and then there was a training phase, and then the software could recognize, so for this design I use this algorithm for converging and for the proof. So then the second version of this software, now we said, now let's use the reinforcement learning. So basically now the software starts trying out on a particular design, so which algorithm is the best fit of it, and then so without any labeling. And then using this reinforcement learning, so we got now even better results. So this problem is solved now. The other problem which we have is the regression. So regression basically means that you have a set of verification tests, and then every time when you change something in your design, you always are rerunning these tests, and this can be thousands and 10,000s of tests. And now it always takes a lot of time. It takes compute power. It takes software licenses. So the question is, how is it possible somehow to minimize and optimize the number of regression tests? And this is something that we also are using machine learning for this. So basically, our machine learning algorithms, they are going through all the regression tests, and then they're trying to suggest which regression tests are basically the same, so they can be removed, and also how to optimize the regression tests so that they are covering more cases. So just so just to explain what you see on the picture. So the coverage model basically means that with a certain test, you want to achieve a certain outcome. And so these outcomes, they are in these buckets. So basically, you want to cover all these buckets. So that means that you have covered all inputs and all outputs of a system. So you have verified them. And so therefore, so now you start writing your tests with different inputs variables, and this is how you create your regression tests. And so now with machine learning, so the machine learning algorithms, they have evaluated these tests, and now they are trying to optimize this. And so what we see here, that the number of tests is now lower, the number of runs is lower, and instead there are some buckets which are now covered. So that means that now the regression, so the verification is even better than before. Yeah, so this is just a short overview. So what kind of software Cadence is providing for the industry. So now a couple of words about Cadence as a company. So who we are. So we are based, so our headquarters is in San Jose in California. So Cadence was started in 1988. So it was a merger of two companies. And so now in the meantime, so we have offices all around the world. So here in Europe, we have offices in Munich, so where I'm coming from. We have offices in UK, in France, in Israel, in Sweden, in Poland. So, and our offices are very multinational. So just in Munich office, we have around 40 different nationalities, also people from Serbia working there. So it's definitely possible to apply for a position, even if you are in Serbia now, but then you will be transferred to one of our offices in Europe. So in total, we have around 9,300 employees, and the majority of them are engineers, so who are either developing our software or who are supporting our customers on site, because the software is complex, and therefore you always need support. Yeah. So so what kind of engineers do we need? So you see that our software, we call it, it's a software for intelligent system design. So that means our software needs to be intelligent. So there are a lot of different algorithms which are needed to be implemented for different problems. So there are a lot of optimization algorithms. There are a lot of algorithms for how handle operations with matrices, how handle them efficiently in the cloud. So how do you parallelize a problem with big data? So there are many different interesting problems to solve. So here are our software that we are providing. So so you see there is intellectual property. So these are parts of the chip which we are providing then to designers. So for example, we have a processor which is optimized for media handling or for computer vision or for AI. We have digital software, so like I already mentioned, Genus Innovus, system verification, so like the Palladium and Protium, and also Xcelium, Jasper for formal verification, for digital simulation. Then we have software for analog design, Virtuoso, for packaging and PCB. And recently we also started doing a multi-physics system analysis. So if you can simulate how hot your system is becoming, or does it radiate electromagnetic radiation, or also CFD, so computational fluid dynamics. So all of this software is now also part of Cadence, and we are providing this to our customers. Yeah, so so many companies say, so we are a great place to work, so come to us. And we can actually prove that we are a great place to work because there's an organization which, so it's a worldwide organization which every year is doing a surveys among the employees of the companies, and also you have to write a report. And then there's a ranking, and this is called Great Place to Work. And Cadence is participating in these surveys and writing these reports. And so we are regularly on top positions in different countries. So it's basically a kind of a proof that it's really a place to come and also to stay for a while. So Cadence is also a responsible company in the sense that we have committed ourselves to reduce emissions of CO2. So we have a foundation, so which takes care of different social projects, and we are also taking care of diversity, equity, and inclusion. Good. So this is the end of my presentation. So I don't know. Do we have time for questions or? Okay. So any questions? Sorry? It's clear. Okay, perfect. Good. So, okay. So in case if there are still questions, so I'm here at the booth. So till today afternoon, so you can just come to my booth, and then we can also discuss individually. Okay. Thank you for your attention.